So previously, we looked quickly at the first ionization energy trend. This is one of the periodic trends that you can try to explain with the general rules of effective nuclear charge. So that's looking at number of energy levels / shielding effect and the number of protons to try to explain why electrons would be more or less attracted to the nucleus. And when you look at this trend, in general, it follows those rules, meaning that as you go from left to right across the table, you do see a general increase in ionization energy, which we can explain by saying there's the equal energy levels, so an equal shielding effect, but we have an increasing number of protons that increases the positive charge in the nucleus and therefore it increases the effective nuclear charge, the ZEF, as we call it for shorthand. But what those rules can't explain are why there's a dip here, which we see both in row 2, period 2, and then again we see it in period 3. And they also can't explain why there's a dip here and there's a dip there in between those elements. And so for those, we were waiting until after we looked at the electron configurations, and we talked about orbitals, and now we're going to see if we can come up and suggest more specific explanations for why those little discontinuities in the trend happen. So that's what we're trying to explain now. I'm going to start by trying to explain this first one. Okay, we know that we can't just explain this with protons. If we could, it would be a general increase from left to right, but we see that boron is lower than beryllium. So we want to look closely at their electron configurations. For beryllium, we end up with 1s2, 2s2, whereas for boron, we end up with 1s2, 2s2, 2p1. So now that we're looking at specific energy sublevels, which is what the S and the P are in electron configuration, the thing that jumps out at me is that boron has an electron in the 2p sublevel and beryllium doesn't. So let me try to turn that into an explanation for why it takes less energy to remove an electron from boron. Well, the 2p sublevel is slightly farther from the nucleus than the 2s sublevel, or the 2s orbital. That's something you could say. Along those same lines, if you wanted to go a different direction, you could also say that therefore the 2s causes a slight shielding effect on the 2p electrons. Okay, if an electron is farther from the nucleus, or if an electron is more shielded from the nucleus, either way, that electron will experience less attraction. So either one of these things you want to say, or both of these things if you want to say it, we would say the electron in the 2p of boron experiences less electrostatic attraction or to the nucleus than the 2s electrons in beryllium. So if we're giving a really, really thorough 2-mark answer, I would say mark 1 is over here. Either one of those points should earn you a mark. You could probably also write out the configurations to help you, right? But pointing out very specifically, this is the difference between 2p and 2s. So something about how there's a difference in the distance, or something about how the 2s shields the 2p very slightly. Either one of those reasons could be given for why the 2p electron in boron is less attracted to the nucleus. If it's less attracted to the nucleus, it will take less energy to remove it. We could apply these same arguments to try to explain why it's easier to remove an electron from aluminum than magnesium. So this is a great 2-mark explanation for that discontinuity, for this weird irregularity in the first ionization energy trend. If we move on to the next discontinuity here, so I'll circle these ones in purple, we're going to have to use a different line of reasoning, because when we write out their electron configurations, I get that N is 1s2, 2s2, 2p3, and oxygen is 1s2, 2s2, 2p4. So if I look at them right away, they both have the same sublevel. They have electrons in the 2p. So that's not really going to help me. I don't have s versus p here. Okay, so now if I'm going to try to break it down, I actually need to look even closer. And if I look at their orbital diagrams, and I look at these box and arrow diagrams, I would see that in nitrogen, all of the electrons are unpaired. But in oxygen, there is a pairing of electrons. And that's what we're going to focus in on to make our argument, to make our case for why it's easier to remove an electron from oxygen than it is from nitrogen. So I can see the value for oxygen is lower. So I would say that in oxygen, it has paired 2p electrons, whereas in nitrogen, they're all unpaired 2p electrons. Well, as we saw with the radii of anions, of negative ions, those additional electrons that are right next to each other, that creates repulsion. And so the paired 2p electrons creates additional electron repulsion, which is probably going to be key to you getting the mark, saying electron repulsion. So getting across the concept of unpaired versus paired electrons is probably the first mark. And then for the second mark, we're looking at how that creates additional electron repulsion. Repulsion is essentially the opposite of attraction. So because there's extra electron repulsion in oxygen, it takes less energy to remove an electron from oxygen than it does from nitrogen. Even though oxygen has an extra proton, that electron repulsion seems to outweigh it for at least this first paired electron that we see in oxygen. So additional repulsion is equal to less Zeph in oxygen. So we could also use that same argument if we were talking about sulfur versus phosphorus. Again, it's the addition of that p electron. For the first time, the p electrons are paired, and the pairing of the p electrons creates enough repulsion that it outweighs the additional proton that we're adding to the nucleus. Therefore, the extra repulsion seems to be lowering the attraction towards the nucleus, and the electron is more easily removed. So you would be expected that you could come up with a 2-mark answer for either one of these discontinuities in the trend across the periods. So either the one here or the one here. They have distinct reasoning. You'd also be expected to be able to pick out the correct reasoning on a paper 1A question.